Right-hand rule, talking about the the magnetic field around this current carrying wire. Blake, you said it's, so below the wire, it's going into the page. Above the wire, it's coming out of the page. So it's looping around this way. And we use the right-hand rule to figure that out. It's going over the top, it's coming around the back. What happens if I take that wire now, and I don't know why this is missing. Just redraw that in there. That should be a loop, closed loop. We take that wire and we fold is the wrong word, but if I say fold, are we cool with what you understand what I mean? We don't fold hoses, but we coil them up. So, but there's a folding motion that has to happen there to wrap the wire back on itself. So if we do that, what happens? This stage of the wire is going to be dealt with exactly the same way. It's going to come up from the back over here, and it's going in over here. Let's keep that path going. It's going in, and then as I travel along the wire, sorry, it's coming out. The dots are out. Out, 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 out. And then as I followed that loop, right? It's like a roller coaster. I mean, using the right-hand rule, we could prove it too. At any stage along the wire, at this point right here, the current is going this way, so my fingers are going to curl up through the middle of the loop, which is going to be the same any stage around that loop. You can think of like running your hand around that ring. At any stage, you're going to get the magnetic field coming up through the middle of this. And likewise, we could follow that same path for the magnetic fields going in everywhere around the outside of that thing. It'll stop looking like X's at some point. So everywhere around this loop, we've got the same situation happening here. That's interesting. These are vectors. We've seen when we got multiple vectors in an area, they all going in the same direction, they start to add. So if I start to coil this wire up multiple times, we're going to start to increase the effect of the magnetic field along, or at least through the center of what is eventually going to be a large coil. You can think of like a slinky. So we can see that the field of all the current bits is the same direction. This means that inside the loop, we're concentrating the field, like I've already said. We wind a large number of these loops in a wire. What we can make is a coil, or a solenoid is the technical term for these things. Inside the coil, all the loop fields point in the same direction, so they add, creating a large resultant magnetic field. You can take a relatively small current and make a massive, relatively speaking, magnetic field simply by coiling the wire on itself, summing up all of the individual magnetic components. Sorry? Why are you throwing a magnet inside? Wouldn't it? Would it? No, you're not actually being dumb. You're actually, what you're discussing is where we're going next. Oh, okay. Next chapter. There's a process there called induction. So we want to draw the direction of the fields around the individual wires. You asked the question, but it's actually the next chapter. For each one of these wires, as the current is going up over the loop this way, it's coming out of the page here and going into the page here. For this wire alone, what's the direction of the magnetic field? Does it move? Yeah, the magnetic field is going which way? So it's going over and around that way. Is that what you're suggesting? Okay, so it goes over the top this way and in that way. This wire is going to do the exact same thing. This wire is going to do the exact same thing. This wire is going to do the exact same thing. So what you're going to end up having here is these guys are all going to start to stack and add as the individual wires do their thing. Up over the top, in behind. Up over the top, in behind. You're going to get a large magnetic field traveling to the left through that coil. Part B we just did on A. I just drew the individual contributions are going to give us the one big one. The field lines on the inside and the outside of the coil, if I've got magnetic fields going this way, talk to me about where the poles are on that magnet. Because effectively what I've done now is I've made a big magnet. So this would be our, which pole's going where? What happens at a north pole? Magnetic fields go out of a north pole. So this is north. Coming out here. So this is our north pole. This is our south pole. They're going in over here. So what with a solenoid here, what we've got is our magnetic field would loop around. So whether it's a bar magnet or a solenoid, effectively it's acting the same way. Your bar magnet is solid all the way through. Your solenoid is like a weird donut. There is a new right-hand rule, the second of three that we're going to look at. The first one was for an individual wire. You put your thumb along the direction of the wire. Your fingers then give you the direction of the magnetic field as it loops around a single wire. The right-hand rule, this is the right-hand rule for a coil. You go the opposite now. Now your fingers are going to be traveling in the direction of the current in the wire as that wire is coiled on itself. So our fingers then are going to form the coil. Your thumb becomes the direction of the magnetic field. So it's the right-hand rule for a coil. We had a right-hand rule for a wire. Thumb was wire. Fingers were magnetic field. Now, for a coil, fingers are the wire and the direction of the current in that wire. The thumb is going to give you the direction of the magnetic field now. Keeping these right-handed rules straight is going to be important, perhaps something you might want to toss in the back of a formula sheet. So if we flip the page, let's practice this thing. Using the right-handed rule, the new right-handed rule for a coil, what's the direction of the magnetic field for this guy? It's incorrect, sir.
Or wait,
which way is the...
Yeah, it's going to the right.
These things are looping, so the new right-hand rule,
Yeah.
It's going into the... My fingers are going to go into the page, come up, and go around.
Yeah.
So my magnetic field is going to the right. So my B field is going that way. Yeah, it's like those optical illusions. This way is the dancer spinning. Is the dress gold or blue? But it's actually, that's the kind of question you would ask on a test or a quiz. I'm having trouble seeing the direction of the arrows for the current. I will happily tell you which way the arrows on the current are going, if you're having trouble wrapping your head around that. So if this is another coil, again, it's one wire, but basically what the idea here is that you've got a bunch of rings vertically. See, I could have, one finger, or I could have like 1,000 fingers. It looks exactly the same, doesn't it? Totally. So I take my direction of my current in the coil. That becomes my fingers. So which way is my thumb pointing? up at the camera, which is up out of the page. Magnetic field, how do I draw that? Big dot, or a whole bunch of little dots. That's my B field there. So my B field must be going in everywhere else. Zach, you asked a question you thought was stupid. You were wrong. If we place a piece of metal, so not specifically a magnet, but a piece of metal, iron is usually the metal of choice, which makes these things pretty heavy. Inside that coil, the iron and the coil together form a much stronger magnet. This is the basis for an electromagnet. Because what the magnet does is the magnet actually helps the particles of iron align with the magnetic field. And so not only do you get the magnetic field generated by the solenoid, but you get the magnetic field generated by the iron itself. And so you get this massive electric field as the hunk of iron and the magnetic field in the solenoid itself add. No, you could physically wrap it. If this bottle is my iron core, you just wrap it in there tight so it holds. It's not being suspended. It's part of the construction. So applications of these things, you've seen them before. If you've ever seen the movie, if you've never seen Gone in 60 Seconds, like that to me is the classic car movie where we're lifting cars and junking them. Everyone needs to see Gone in 60 Seconds. It's like Nicolas Cage's greatest movie. Scrap car being lifted by an electromagnetic. We've seen these before. Another example of this is the bullet train technology. Bullet train technology is fantastic because there's no friction between the track and the rail. They just use alternating magnets, turning them off and on really, really quickly. Mrs. Dona's dancing down the hallway. She's pushing someone down the hallway. We're not going to ask the question. Crystal's going to go figure it out. By alternating power in these magnets, what ends up happening is when this one turns off, this north is attracted to that south. That south is attracted. So all of a sudden you get magnets that are just dragging this thing forward. And it goes faster and faster and faster and faster and faster. And basically the limit to the top speed of these things is the rate at which you're turning these magnets on and off, combined with the natural, when you start like hundreds of kilometers per hour. And then you're starting to take into consideration the forces of friction due to air resistance, drag on the outside of the train, which is why they all have these really long noses, because they want to reduce that drag as much as possible. So you get these trains traveling at, I want to say 500, 600, 700 kilometers per hour. It's insane. Because there's no friction between the rail and the car itself. So you just go. There's nothing to grease. There's no bearings. You fly. Slow down is exactly the opposite. What you want to do is then start to you alternate it so that you start to drag the train backwards. And so you can decelerate this thing fairly gradually. Because again, it's not the fact that you're traveling at 700 kilometers per hour that's the problem. It's the fact that eventually you need to go zero. And the transition from 700 kilometers per hour to 0 kilometers per hour is where there are problems. And so, I mean, all of this is regulated by fairly powerful, very accurate computers. And again, all of this is driven by flicking switches on and off really, really quickly, which computers are really good at. So they're electromagnets. You just turn off the current, and all of a sudden there's no magnet. All of a sudden there's no magnet. Okay? These aren't bar magnets just sitting here. These are magnets that you run. It's this. I take my finger off the switch. The switch is now open. Electric current stops immediately.
And then does this also mean realistically anybody in here can make their own magnet for electromagnet?
Yeah. You just need a piece of iron, some coil, and a power supply. Was that a hand? Okay. I mean, with the proper amount of materials, you guys can make a staggering amount of things. And it's the realization, and that was part of the transition for me as a high school student through my university career. Like, I took courses like this, and you're sitting there and you realize the things that I have just learnt, the only thing that's stopping me from building some of this crazy stuff is materials. I had buddies who took nuclear physics courses. The only thing stopping, like, at the end of an undergraduate nuclear physics course, they had the knowledge required to build a device that could undergo fission, i.e. a bomb. Okay? The knowledge to build an atomic bomb is taught at the undergraduate level. The only thing stopping you is access to the materials. Yeah, it's time and monetary constraints. Can you pay enough? You have the required materials. There's no reason why you too could build an electric train. A more entertaining version of this same technology, let's call it Gauss gun or a rail gun. Where you're not actually building, and where the gun itself doesn't have bullets that are gunpowder explosive. Basically, the premise here is I just got a big rail, a hunk of metal, can be very heavy. And using an electromagnet or a set of electromagnets, you can accelerate that thing really quickly. The damage that a flying hunk of metal can do at thousands of kilometers per hour, you don't need it to explode. You just need it to make contact with anything. And that thing that it's making contact with will no longer exist. Anyone who ordered copies, so. So sick. It's just so cool. Yeah, what do you mean? That rail come in?
Dynamics, kinematics,
And then the only constraints are how much power you need.
it's so cool. Okay, but I feel
You're going to learn very quickly that lots of the problems that are faced all come down to cash. Cash and availability of materials. That's it. Yeah, that's why we're using iron. It does, but it's smaller compared to the strength of the coil.
And then with the coil, it's just coil.
Copper wire?
Yeah.
That's all you need. Well,
Or like,
different materials will run it better.
okay.
Gold is a better conductor than copper.
Okay.
But copper is a phenomenal conductor. You don't need to be better. Anyone who's like, yes, it's that's how they scam you with like sound equipment. I can buy this cheap wire made of copper, or I can get my gold-plated things.
Oh.
Is gold a better conductor? Yes, objectively it is. Is that going to change the quality of your sound? No, they're screwing with you. But it is objectively a better conductor. You don't need it though. Okay.
Like beneath its frame.
Yeah.
That you could turn on and off. I feel like does that not pose extra problems? Like there's so many things that can go wrong. Like what if they fail? Well, that's why they have.
If the computer fails,
Yeah.
Obviously you'd have to have built-in safeguards. When the thing locks down, like what you'd have to have is, in the event of a failure, power failure, whatever. Well, power failure, the thing's going to drop. Well, it's not bad. The way these things are designed, it looks like this. No, the way the trains are designed is your train car looks like this on the bottom. And the rail looks like this.
How do they stay on the track?
So you get this thing that levitates just around this inner T. So if the power fails, it's the perfect safeguard. Power fails, train's going to drop onto the rail, and then friction's going to make sure that train stops. You're going to have, it's going to do damage certainly to the underside of the train, but the worst case scenario, you grind to a halt, literally. And that's great. Yeah. Yeah. We're not. Yeah, the suspension's not very high. You don't need it to be very high. You need to hover. Again, assuming those surfaces are smooth, an atom's width would be sufficient, assuming perfect smoothness.
But when
So then you give it a little bit more, then you give it the leeway, and yeah, you can bounce a little bit there, but again, the strength of these magnetic fields, you can push down pretty hard on top of these trains, and you're not going to come close to the strength of the repulsive between those magnetic. And again, all of this is tuned really specifically. Those of you guys are going into engineering, you're tuning things perfectly, or you're supposed to, as an engineer, be tuning these things perfectly. You're looking at the mass of the train, fully loaded, empty. How much power do we need? Where do we fluctuate the power to create the strength of magnetic field necessary to create the repulsion that we need, and dragging this thing forward? How do we alternate the power in these different, like, all of the problem itself becomes really complex from an engineering standpoint. The physics is simple. That's why they pay the engineers the big bucks, because they take a relatively simple physics phenomena and they do cool stuff with it. The process of making that happen, again, time and money. In this case, belonging to the engineer, which is why they get compensated for it. Because this isn't easy. Conceptually, it's simple. Practically, to do it safely, it's a substantial undertaking. Old school doorbells work the exact same way. An electric switch, when the coil is on, its magnetic field pulls the contact and either breaks the either makes or breaks a connection. An example is a doorbell switch to the right. This guy here. When the switch is closed, if you have like your doorbell switch here, when I close it, I push the switch. This coil pulls this contact back. As soon as I let go of the switch, breaks circuit, magnetic field stops, ding.
Oh, so if you hold it, it won't.
Well, if you hold it, it depends on this is super simple. Depending on how the inner workings are going, if it's ringing constantly, again, assuming it's not just an electric buzzer,
right?
Because that's an entirely different. This is old school tech. But if you want this thing to ring back and forth, you could move some stuff around. You could put the contact inside the bell. You could have it so that when you push it, it alternates it back and forth really quickly, like AC current, so that it would turn it on and off really quickly so that the contact's ringing back and forth. So you'd have a rapid dinging, ding, 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 as this thing moves back and forth. This is a physical, this is a physical bell, old school tech. That's not actually that old. Like, this is how the doorbell in my house growing up would have worked. On the wall, there's a plastic box. There it was. I could see the thing. You push the doorbell. That happens inside. Well, with COVID, you can't, go to people's houses, so doorbells don't exist anymore, really. In a useful form. Okay, now you're talking. Now that's just an electrical. It's a computer. There's a circuit board in there. You push the button. Tells the circuit to play a song. It's a speaker. It's like hitting play on Spotify, and it does your whatever program tone is there, and then it ends and it's done. Not even remotely connected to what we're doing. That's just that's very different. So the field of the coil, strongest inside and at the ends. The direction is along the axis of the coil. Comes out at one end, goes in at one end, comes out at the other. This is not. We've said this already, so I'm not going to necessarily draw it again. This isn't a simple bar magnet north-south dipole, but we label it like it is because effectively it functions the same way. I've got a north pole here. I've got a south pole here. So if I've got this coil and that magnet, what's going to happen with them? Are they going to attract or repel is the question. How do you know, Nathan? Show me. What did you do? I saw you do something with your hand. So it's coming up the back and down into the front, so my magnetic field's going to the right. If my magnetic field is going to the right, what pole is this? This pole is. So if I had this bar magnet sitting in this solenoid and I turned the current on, that magnet's going to go flying which direction? To the left, very aggressively. It's repulsive here. It's not difficult to do. I've seen a middle schooler do it for a science fair project. When I was at UFV, they had the physics students go judge. The senior physics students got to go judge the Fraser Valley Science Fair. I saw some cool stuff. One kid made a middle school kid made effectively a gun. He shot nails. It was wild. I got to play with it. It was awesome. But yeah, I mean, his dad was an electrical engineer, so the kid obviously had help. He didn't win, but it was cool. We were shooting balloons with his gun. It was cool. I don't remember the winner. We voted. There was I don't know. They had the senior biology, senior physics, senior chemistry, senior math students go judge these things, and it was pretty sweet. There is a relationship. Now we've talked about conceptually how this thing works. There is a relationship, mathematical relationship, that determines the strength of the magnetic field in a coil like this. The magnitude of the field, or the strength of the field, depends on a few things. Obviously, it's going to depend on the current, and it depends on the concentration of the loops. How many loops do I have? How tightly are they wound? You can think of this concentration of loops as a loop density. If I use this word density, are we cool with what that means? How much is packed into the volume that's present? The more that's packed, the higher the density. The less you have, the less dense something is. I'm not even going to get you to derive this. I'm just going to tell you what has been experimentally validated. B, the strength of a B field, is equal to mu naught. It's not a coefficient of friction. I'll tell you what that is in a second. Times big N times capital I divided by L. So let's do this. Joseph, you just asked, is capital I current? Yes. We are consistent with that. Capital I is current as established by the unit that is now in Physics 11, circuitry. This chunk right here is the loop density. It's the number of loops divided by the length of coil. Length is always measured in meters. And then this bad boy here, mu naught, has a name. Well, K had a name too. I didn't tell you what the name was. Mu naught. Oh, why is my internet not working? Come on. Yes. This is the permeability of free space, or the permeability of a vacuum. How easily you can flow, or how things flow through something, is how permeable something is. So the permeability of free space, or a vacuum, that's the name of that constant, and it's given to us with this value here, 4 pi times 10 to the negative 7 Tesla meters per amp. Yeah. It is on your formula sheet right there. That is the permeability of free space. Oh, and the K constant from before, this guy here, that is just called the Coulomb constant. Nice and easy. And yes, it has this value, but it's based on, well, that number comes from 1 over 4 pi epsilon naught, and epsilon naught is related to mu. So actually, K and mu are related to each other, which is pretty cool. Mu naught, this guy here. K and mu naught are related. Oh, man. And that's related to the fine structure constant, the elementary charge, the Planck constant, and the speed of light in a vacuum. This is, oh yeah, things get wild. As you get further and further into these things, these constants and how they came to be, things get wild. But we're not going to do that. We're just going to use this now. Let's go look at some coils. So I've got this coil here. I want to find the field and the direction of that field at points X and Y. The coil has 600 loops and carries 20 amps. 20 amps is a lot. That's a lot. To put that into perspective, when you plug your phone into if you have an iPhone, I don't know what the Samsung ones are, but I do know that the iPhone blocks, like the lightning things that you plug into the outlet, that produce a current of 1 amp. Okay, to charge your phone, so as not to blow up the battery. This is a current of 20 amps going through a 600 loop coil. Direction of the field, first thing. Which way is it going? Are we all in agreement that this thing's going to the right? Okay, I saw a whole bunch of right-hand rules. Carl's doing it. Carl's pointing to the right as well. We love it. So that is the direction of our B field. And now the strength of that B field is given to us using mu naught Ni over L, which we can just plug those in and go for it. 4 pi times 10 to the negative 7 times the number of loops, 600, times the current in those loops, 20 amps, divided by the length of my coil, and that coil has a total length of 4 centimeters. 0.04. Like the physical length of the coil. You pull out your ruler, you measure the... No, not the total length of the coil itself. How tall is the slinky? Not if I deformed the slinky. It's the slinky is stacked. How tall is it? What's the strength of my magnetic field there? I also got, is it 0.376 what?
9.
So 7. Can anyone verify that Zach got the same thing? Or that got the same thing as Zach, rather?
My calculator doesn't like 4 pi e.
Doesn't like 4 pi e7? 4, oh no, I don't want that. 4 pi e7. Oh, my calculator will do it. Make sure that you can actually calculate the same value Zach got, because I'm confident Zach's value is correct.
0.377.
There you go. Okay, 0.377. And we're going to go back up here for a sec because there's something I forgot to add. This is an important fact. Just like parallel plates having a constant electric field throughout, the B field is constant everywhere in the coil. It doesn't matter if you're right near the edge. It doesn't matter if you're smack dab in the middle. It is equal everywhere inside. Just like parallel plates had an equal electric field everywhere. Units on which? Teslas.
Okay.
Units on B field strength is Teslas. Okay, flip the page. There is an alternative formulation for the same thing we just looked at. For some coils, instead of being given the number of loops and the total length, instead they give you the ratio. The ratio is little n. Little n is equal to big N over L, which is loops per meter. So I could give you an example like 6, and I say find the field and the direction at the center of a coil. The coil is carrying 10 amps of current and has N equals 2,500 coils per meter. So they don't tell you how long the coil is. They just tell you what the coil density is. So this would become, so B equals mu naught Ni over L is going to become mu naught little n times I, where n over this n over L piece is going to become little n. And so that's why I wanted to call it a coil density earlier, because sometimes they just give you the coil density, the coils per meter. Mu naught, that little subscript 0 is read as whatever comes before it, naught, N-A-U-G-H-T. N-A-U-G-H-T. That's a... We'll leave that for now. We'll leave it for now. It means 0 or null is effectively what it's meaning there. So mu naught being, and there's all sorts of, it's used for different things in different places. Sometimes it's used to represent the 0th state of something, like the resting state of something. In that case, so it's called like x sub 0, or x, but it's read as x naught, N-A-U-G-H-T, naught being null, being 0, all those things meaning the same thing. So that's how it's read. So the permeability of free space is mu naught, free space being empty. And mu theoretically being connected to friction. So how friction in a vacuum or drag in a vacuum is the permeability of a vacuum, hence the mu. Yeah, AJ?
Is that like a null hypothesis? Like null is 0?
Null and 0 are different. Technically, they're different. So we can run it the same way though, using coil density instead of N over L. Coils per, the turns in a coil per the length of the coil. We can just run this as 4 pi times 10 to the negative 7 times the 2500 coils per meter times the amperage. Strength of that coil is going to be what?
0.31415.
Well, let's stop it there. 0.0314 Teslas. And what's the direction? It is, in fact, out of the page. And the interesting thing here is, given the coil density, it doesn't actually matter how long that coil is, as long as that density remains the same. The coil could be 1 kilometer long, or the coil could be 6 inches tall. If the coil density is 2,500 coils per meter, it's going to give you the same strength of magnetic field regardless of the length. Which is why giving it to us in this context is still a useful result. It's a useful procedure to do. Flip the page. You're still getting syntax errors? I think I have that same calculator, Nathan. Is it this one? Is it the Casio?
Yeah.
Okay. I got, where's pi? Where?
Over where that's at the bottom.
How can I not see this? Oh, here. So 4 pi negative 7. Ooh, syntax error. Interesting. So 4 times
I had to do
pi
times 4.
to the negative 7. Interesting. So what if I go...
Yeah, I did pi times 4.
Interesting. I don't know why your calculator has a problem with that. Okay, next example. The coil below shows a compass needle pointing north in the Earth's magnetic field. If it's pointing north in the Earth's magnetic field, what can you tell me about that coil right now, in this state? It is off. There's no current flowing through those wires. Once the current is switched on, which of the following is most likely the angle at which you will find the compass needle? So, let's rule out, there's I options there. let's get rid of that. Let's get rid of a bunch of these. What do we know is not going to happen to this coil? It's likely not going to stay pointing north. Well, which way? Let's look at it. Let's look at it. Which way is the magnetic field pointing? Once we turn this thing on, it's going to the left. We don't know how strong it is, but we know it's going that way. So let's rule out some options here. We know that, and this is, if it's going this way, which pole is north and which is south? So my north pole is there, my south pole is there. So the north pole of my magnet's going to be attracted which direction? Sorry? It will point in the direction of the compass will follow the magnetic field. So it's going to go, yes, it's going to go left. So we know it's not north. We know it's not east. It's not north of east. And it's not east of north. Oh, it's also not northeast. So let's talk about those other options. We got C, E, G, and I. Give me some reasonable arguments for or against any of those four options. Well, through the middle here, it's all going that way equally. So let's draw some stuff in here. If we know this is this way, the compass is pointing that way, we know that the B field from the Earth is going this way. Just because, and I'm going to call this B coil. So the compass is pointing along with Earth's magnetic field. We've got a south pole up at the top. Those are attracted to that south pole up at the top. So the B field from the Earth doesn't disappear. It's just, relatively speaking, weaker. We do have values for the B field of the Earth. Well, and we saw what happened when a single wire had a current running through it. We've got a coil now. So we can get rid of northwest because it's not going to be pointing this way likely. We can get rid of 10 degrees west of north. That's just a little bit of a deflection there. So your most reasonable answers are C or G. Dependent on what? Dependent on the strength of, well, we know what the strength of the Earth is. It's the strength of the coil. It depends completely on how much current you're running through that coil and the density of the turns in the length. Because you're going to have something, yeah, you're going to have something that looks like this. You're going to have the B from the coil, and you're going to have the B from the Earth. And like vectors have done this whole time, they're going to add. As the B field gets from the coil gets larger and larger and larger and larger, the relative size of this arrow is going to do what? It's going to shrink and shrink and shrink and shrink and shrink and shrink. So if you could argue C or G. If you can pump up this big enough, the strength of this isn't going to impact the resultant vector. This is much. It's got to likely lay flat. But you could also say, you know, if the current in the wires isn't that big, or the coil density isn't that big, you're still the Earth is still going to provide enough of a field in that direction to give it a bit of a deflection. So 10 degrees north of west is also totally reasonable. You could argue either one of those fairly successfully. Comments, questions, concerns? Okay, play with it. Flip the page. Here's what I want you to work on. I'll give you some time to do it. I want you to do, I have it written here. You think you know what it's going to be?
Yeah, I do.
It's 1. It's 3. It's 4.
You say all also said 2 though. Yeah, you did. Yeah, you did. 2 plus 1. Oh, okay. Oh, thank you. Yeah, so we got that other formula for formula.
Which one? Oh, yeah, that's a good idea. This guy here, bottom of your formula sheet here, B equals mu naught N over L times I. Let's add the other one that we have. B equals mu naught Ni. Right below it, where N over L, big N over L, is equal to little n. Little n being your coil density. Yeah, 1, 3, 4. Man, do I want you to do 5?
No.
Yeah, I want you to do 5. And 6 is easy. That's it. You're done. Like 5 and 6, you're just drawing arrows on pictures and right-hand ruling things. The only calculations you actually have to do are 1, 3, and 4. Give it a shot. This should not take very long. See where you guys are at in 20 minutes.